Now, linked in with the product rule is also the quotient rule. So if we have one thing divided by another thing, then we can use this rule to find out what its differential is. Now, also, using the rules of exponents as well, we could also say this is u, and then whatever the bottom is, v to the -1. And then actually this would turn into a product rule. Now, I would try and avoid this. If you have a quotient, then leave it like this and try and work it out in this form here, rather than change it into this type of question. The other question you should try and avoid for also is when we have something like that. If we have just our top term as just a constant term, then we don't need to use the quotient rule either, because actually for this question we can bring this to the top. So we can say this is x plus 3 to the -7, and then we can just simply use our chain rule to differentiate this. Bring the power to the front, decrease the power by 1, times by the differential of what's inside the parentheses. So there's a couple of cases when you should try and just make sure you know exactly what you're using this for. Now, this question is actually very good for answering this type of question. Now, to begin with, that actually doesn't look like a quotient rule question at all. But we can actually go ahead and prove what the rule for this is. So using the definition of cotangent, which is cosine x over sine x, then you can actually see that we do have a quotient here. So if we set our top term u equals cosine x, and when we differentiate that, we get negative sine x. And our other term is the denominator, which is sine x. And the derivative of sine x is positive cosine x. Then using this formula, we can start to work out what the actual differential would be. So v times du, so this times this. So we have negative sine x times sine x, which would be negative sine squared x. Subtract u times dv, so cosine x times cosine x, which would give me cosine squared x, all over v squared. So in other words, all over sine squared. Now, I can see that both terms on the top have a negative, so if I was to take that out as a common factor, so I've still got negative sine squared, take away cosine squared. And hopefully you can see the reason why I took this as a factor. Look what we have left on top here. This is an identity. So sine squared plus cosine squared equals 1. And the definition for 1 over sine squared is cosecant squared. So your answer is negative cosecant squared x, which is actually what appears on your formula sheet. So if you're ever asked to prove why the differential of that is this, then the quotient rule is a very good way of doing this. And also we can try and do that for all the other rules as well. And you can see videos on how to do that as well. So another ratio we can also use the quotient rule for is tan x. So the definition for tan x is sine over cosine x. So I've called u equal sine x here and differentiated. I've called v equal cosine x and then I've differentiated that. And then using this quotient rule here, I can just substitute those values in. So v times du is these two terms here. So cosine times cosine is cosine squared. Minus u times dv, so sine x times negative sine x, which would be negative sine squared x. Two negatives here we can combine into a positive. You can see this is looking very similar to the last question now as well. Divided by v squared, so divided by cosine squared x. Now our numerator once again is 1. And the definition for 1 over cosine is secant, so this would be secant squared x. So, and as we already know, the differential of tan x is secant squared. And that's one way you could prove that if you were asked to do that. Now, these certainly aren't quotient rule questions. We do have a quotient, but our top term is just a constant term. But just to finish this off to show you the two other proofs. Secant is 1 over cosine, which we could write as cosine x to the -1. So if we want to differentiate this, bring the power to the front, decrease the power by 1, times by the derivative of cosine, which is negative sine x. The two negatives combine to make it positive. And then what we have here is sine x over cosine squared x. And that doesn't look like anything too obvious to begin with, but if we split this up, we can write this as 1 over cosine x times by sine x over cosine x. And then we can start working out what each of these are. So 1 over cosine would be secant, and sine over cosine would be tan. And that's when we actually learned the differential of secant x is secant x tan x. Now we can do the same thing also with cosecant x. So we can write that as 1 over sine x, or sine x to the negative 1. So when we differentiate, we bring the power to the front, decrease the power by 1, and then times by the derivative of sine x, which is cosine x. So what we have here is negative cosine x over sine squared x, and then we're going to try and do the same trick that we did over here a second ago. So we're going to write that as negative 1 over sine x times by cosine x over sine x. So 1 over sine x would be cosecant x, and cosine x over sine x would be tan x. So in other words, the differential of cosecant x is negative cosecant, I apologise, the differential of cosine over sine is cotangent. So the differential of cosecant x is negative cosecant cotangent, as we learnt in the previous section.